Yeah, this is Dr. J. Mohan from EC Department of Institute of Aeronautical Engineering. My subject is Signals and Stochastic Processing. In this topic, I should discuss about the Fourier transform. Already we discussed for the two section. The third section, we are going to discuss about some sample signal regarding to the Fourier transform, what will be going to happen. Today presentation outline is Fourier transform of triangular pulse, Fourier transform of Gaussian signal, Fourier transform of Gaussian modulated function, Fourier transform of one-side real exponential function, Fourier transform of two-side real exponential function, then reference. First, we go for the Fourier transform. The Fourier transform is going to satisfy for the non-periodic signal. It came from the Fourier series only. So, the Fourier transform, we should do what will be going to happen for the some sample signal. Now, here I am going to take for the triangular signal. We know the triangular signal. The triangular signal, it's going to look like a triangular. The maximum amplitude is equal to 1. It's going to have for the both the sides are equal samples. So, for this is the left side, what will be going to have same, it will be going to happen for the right side of together. Now, the Fourier transform, I should use for the rectangular signal. That rectangular signal, I use the represent for the mathematical form as rectangular of t by tau is equal to 1 minus of 2 mod of t divided by tau. For mod of t is always less than of t by tau by 2 or 0 for otherwise for any cases. That means if 0 the amplitude is equal to 1, then remaining portion what will be happen, this total period of t by 2 is represented as a 1 period of t. That t I should write as here is a minus t, sorry, here is I write as a plus t, here is I write as a minus t. So this both the t I should make to write as mod of t. This mod of t is represented as a minus t to plus t. This minus t duration, the case of time period is tau by 2. This case is represented as a tau by 2. This left side I represent as a minus, right side will be represented as a plus. Based on this condition, we make to write for the triangular pulse as del of t by tau is equal to 1 minus of 2 mod of t divided by tau. For t, the t is represented by the minus t to plus t. That's why I write as a mod of t less than of tau by 2. Then remaining portion, all portion, it's represented as a 0. That's why I write as a 0 otherwise. So generally I write for this triangular pulse as x of t is equal to rectangular of t by 2. This is a mathematical expression for triangular pulse. From the definition of Fourier transform, f of x, that is represented as a Fourier transform of x of t, I should write for the Fourier of what the triangular signal we received. The triangular is represented as a triangular of t by tau. So this is a capital letter item. So that should be, I write as a Fourier condition, f triangular of t by tau is equal to x of omega. So actually what the Fourier transform of x of t is represented as a x of omega we write. So that means time domain signal into frequency domain signal to convert for the Fourier transform. Now we know the Fourier transform, the formula, that formula is represented as a minus infinity to plus infinity of integration with x of t e power minus j omega t dt. So now the interval is minus infinity plus infinity. The x of t is represented as a triangular signal. That is triangular of t by tau e power minus j omega t dt. Now this triangular value we know that is equal to 1 minus of 2 mod of t divided by tau. We can write it for the x of omega equal to minus, that is minus into plus into x del of t by tau e power j omega t dt. We should write as minus of tau by 2 0 1 plus of this is 2 by tau. Why? Because of we taken for the only this duration. Okay, already it's going to have a minus is represents plus we got 2t by tau e power minus j omega t dt plus this duration we should write as 0 to t by tau 1 minus of 2t divided by tau e power minus j omega t d tau. Then after that we can simplify for the sequence. So this is minus t by tau by 2 to 0. This is I make to do for the reverse. That is 0 to plus tau by 2. That is I will change bottom to top, top to bottom. Then automatically what will be happen? This minus 1 plus is going to change with 1 minus of 2t divided by tau. Here the e power minus j omega, it's converted for the e power plus j omega. Then there is no problem for here. We should write same like that one. After making to integration, we should substitute for the our limit. Then after substituting the limit, we got the output is the triangular form. That triangular form I should write for the x of omega equal to 0 to integration of t by tau 2 cos omega t dt minus of 2 by tau integration of 0 to tau by 2 2t cos omega t dt. So this is we get to simplification of the integration. After integration of simplified value, we should substitute the limit of 0 as well as of t by 2. Here that next step 0 as well as of t by 2. Then we got the output is x of omega is equal to 2 time of sin omega t divided by omega 0 to tau by 2 minus of 4 by 2 t sin omega t omega 0 to tau by 2 plus cos omega t omega square tau by 2 0. This limit we should substitute for this equation. Finally we got the output is like this form. X of omega is equal to 4 by omega square tau 1 minus of cos omega tau by 2. After this we are going to simplify it. So as the norm of trigonometric condition, after simplification of trigonometric condition, our Fourier transform of triangular pulse is represented as 8 by omega square tau sin square of omega t divided by 4 omega tau divided by 4 whole square into omega tau divided by 4 whole square. So now we know the sin c t is equal to, that is sin c t is equal to sin of t divided by t. So based on this condition, we simplify for this equation. So what will be? Here the omega tau by 4 is there. Here also omega tau by 4 whole square. We take it further. This one is like t. The t value is equal to omega tau by 4. Then we write for the equation as x of omega is equal to 8 divided by omega square tau sin square c sin c square of omega tau by 4 into this remaining one portion of omega tau by 4. We came it down for the next step, that is omega tau by 4 whole square. So that finally we write as our equation x of omega is equal to tau by 2 sin c square of omega t by 4. This is a rectangular pulse of Fourier transform. Sorry, the triangular pulse of Fourier transform. That for triangular pulse of Fourier transform, we should write for the Fourier transform of triangular values. Del of t by tau is equal to x of omega is equal to 2 by 2, that is tau by 2 sin c square of omega tau by 4. Then again we write for the another model of Fourier transform of triangular pulses. Triangular of t by tau, the Fourier transform tau by 2 sin c square of omega t by 2. So then we may represent for the graphical model of magnitude spectrum in the triangular pulse. The magnitude spectrum of triangular pulse is represented as a mod of h of omega. So in this case, the triangular pulse, it will be going to have for the equal amplitude changes from the 0 to 4 pi by tau, as well as of negative side minus 4 pi by tau. There is no changes from the amplitude we got for the one bubble shape of magnitude response in the triangular pulse. Then remaining portion, we get it for the small amount of portion, even though that value is going to reduce it by the tau. This main loop magnitude value is equal to tau. We mentioned for here. So this portion it's getting to reduced, and the next portion, that is 16 pi by tau. This is a 0, started for the 0, 4 pi by tau, then 8 pi by tau, 16 pi. It's keep on, it's going to decreasing, but it will be not touched for the 0. So it's going to happen for the left side and right side, it's both will be similar. This is a graphical representation of magnitude spectrum of triangular pulse. Next case, Fourier transform of Gaussian signal. We know the Gaussian function. The Gaussian function is represented by the exponential order. The Gaussian function I should write for the mathematical expression as g e of t is equal to e power minus a t square for all value of t. Here a is represented as a positive real constant. T is represented as the limit, minus into plus limit. From the Fourier transform definition, x of omega is equal to Fourier transform of x of t. That x of t here we got for the Gaussian value. The x of t is equal to g e of t we write. This g of a of t is represented as e power minus a t square for all value of t is going to satisfy. So based on this condition, I should make to take for the Fourier transform the x of omega equal to Fourier transform of Gaussian function value e power minus a t square. So that value you should substitute for the insist of x term in the Fourier transform. That is integration of minus into plus into e power minus a t square e power j omega t dt we got. Now we need to simplify both this of the e power terms. That's why we should simplify inside of integration the x of omega equal to minus into plus into e power minus a t square plus j omega dt. Now in this term we have the constant except for the t, so that's why we take it out for those things. So that will be e power minus omega square divided by 4. We take it out. The remaining portion we should write it for the inside the integration, minus plus into e power of minus t by root 2 plus j omega by 2 root whole square. That whole square here I take for the mod value because of both the negative as well as the positive is present. Now in this case, this term I should take for the u, then du is equal to root of a dt. So this those case you should substitute for here. This term I should substitute u. This term I substitute for the du by root a. Why? Because of du is represented as a root of a dt. This we need for the dt only. This a, that is root a, came for the left side case of denominator. Then we should modify for the equation based on the substitution value of u du by root a. Insist of dt as well as of exponential case. So e power minus of omega square by 4 integration of minus plus into e power minus u square divided by root 2 du. If we make to differentiate and substitute for the interval, we get it the output is like this form. What the condition? So we know this term is represented as the integration of minus plus into minus of u square du is equal to pi. That pi is root pi. Okay. So we should substitute here. The remaining portion we take it out as constant. So now the Fourier transform of Gaussian pulse x of omega equal to e power minus omega square Fourier divided by root a into root pi. Now, this root pi and a are common things. That's why I represent as a constant root of pi by a into e power minus omega square divided by 4. The Fourier transform of Gaussian function is represented as a Fourier transform of e power minus a t square is equal to root of pi by a e power minus omega square divided by 4. Or we should write for the another form also. E power minus a t square Fourier transform, that is, this side is Fourier transform, this side is not as Fourier transform, is represented as a root of pi by a into e power minus omega square divided by 4. So now we can represent for the our exponential order of Fourier transform in the Gaussian function in graphical model. The graphical model of Gaussian function, it will be like a bell-shaped curve. So both left side and right side will be other similar case of amplitude or similar characteristics of signal. So the amplitude, maximum amplitude is represented as e power minus a t square. Next, we go for the magnitude response of Gaussian function. The magnitude response of Gaussian function also similar the shape of the graphical representation of Gaussian function. So this is the magnitude is represent for the this portion. What is that portion? Root of pi by a. The root of pi by a is represented as a magnitude response. Then it will be going to response for the both left side as well as right side is same together. Then this is the way we may represent for the magnitude response of Gaussian function. This is represented as a bell-shaped curve is represented as a Gaussian function signals. Next, we go for the Fourier transform of Gaussian model function. What is that Gaussian model function? The Gaussian model function is represented as a multiplication of some cosine and sine term is called for the Gaussian model function. So now we take for the x of t, the exponential case of Gaussian function e power a t square, it's multiplied with the cos omega 0 t. This is we call for the Gaussian modular function. Now we know the cos omega 0 t as per the Euler form. I should write the x of t is equal to e power minus a t square e power minus j omega 0 t plus e power minus j omega 0 t dt. Instead of cos omega t, I should substitute for this value in the case of Fourier transform. Now we need to take for the Fourier transform Gaussian model function. We included for the cos omega 0 t is equal to e power j omega 0 t plus e power minus j omega 0 t divided by 2. Then I should write and make to separate for the real part as well as of imaginary part. This portion is represented as real part, this portion is represented as imaginary part. By using the frequency shifting property, if you are going to multiply with the frequency value in the input side, the Fourier transform in the output side, it's going to shifted version of how much you are going to multiply with the exponential order. That is represented as a frequency shifting property. That property we need to adapt it for here in the Gaussian modeling function. So now what will be happen? If you are taking the Fourier transform of this portion only, is represented as a shifted version of Gaussian value. So what that shifted version? It's represented as a e power, that is Fourier transform of e power minus a t square. Now omega equal to omega 0, and at the same time next side, this one imaginary part also, it's going to possible to use for the frequency shifting property of Fourier transform. This case, the Fourier transform of e power minus a t square equal to mod of omega is equal to omega plus omega 0. The Fourier transform of Gaussian function is represented as a f of e power a t square is equal to root of pi by a e power minus of omega square Fourier we write. Now we got for the shifted version in the Gaussian modeling function. So the x omega is equal to 1 by 2 root of pi by a e power minus omega 0 square divided by 4 plus root of a pi by a e power minus omega plus omega 0 square by 4a. It also to be represented as e power minus of a t square cos omega 0 t take the Fourier transform of forward side is a Fourier transform, reverse side is represented as a inverse Fourier transform. That is equal to 1 by 2 of root of pi by a into e power minus omega 0 square divided by 4a plus root of pi by a into e power minus omega plus omega 0 square 4a. The graphical representation of Gaussian model function and the frequency spectrum we should write here. The Gaussian model signal is represent for the multiplication of exponential signal. That's why the multiplication of exponential signal into cos term. So the cos signal is like this one. We started here. The sinusoidal signal will be going to happen. Here it will be multiplied with the exponential value. Then automatically amplitudes are getting to reduced. It's keep on going together. So left side also we have the same procedure. What will be going to happen in the right side? Same like that one will be going to happen for the Gaussian exponential function. So now in this Gaussian exponential function model signal, we take for the frequency spectrum. That means the frequency spectrum it will be going to happen for the two sides. What are the side? Whether it will be going to have the left side is like this much and the right side is this much. That's why what I make to write the magnitude response of frequency spectrum condition. The maximum amplitude is equal to root of pi by a. Root of pi by a. At the same time, the frequency is omega minus omega 0. For in this omega minus omega 0, that is plus omega as well as of minus omega. The minus omega 0 will be going to happen for the one Gaussian function. That is the first Gaussian function. Second side, that is a positive side, another Gaussian function also is going to happen. This means if we do for the Fourier transform of Gaussian model signal, it's going to produce for the two different kind of frequency spectrum in the magnitude response. The maximum amplitude is equal to root of pi by a. Next case, Fourier transform of one side real exponential signal. Okay, so one side real exponential signal in the sense what is that? Only one side it will be have a real exponential signal. So that's why we need to do for the one side real exponential signal in the sense we know the one side signal we call for the u of t. That means the graphical representation of u of t I should write for the maximum amplitude is equal to 1 up to infinity it start at 0. The remaining portion all it's represented as 0. This is the one side real signal. The one side real signal I call for the u of t. Now if we multiply with the u of t into exponential signal, then we got one side real exponential signal. Now this u of t I write as a mathematical model. U of t is equal to 1 for t is greater than 0, 0 for t is less than 0. So based on this condition we should take for the Fourier transform. We know the Fourier transform is represented as a Fourier transform of what the input we are receiving x of t is equal to x of omega we write. So directly I write for the x of omega. This x of omega is equal to integration of minus plus infinity x of t e power of minus j omega t dt we write. So now here I consider as a x equal to e power a t u of t. Then I should substitute for here e power a t u of t. The interval is minus plus t. Now we go for the one side real exponential. What is the meaning of u of t? U of t is going to work with only the one side of right direction. That will be start for the 0 to infinity. That's why I remodify for the equation on integral level also 0 to infinity e power minus a t e power j omega t dt. That x of omega is equal to, then we can simplify for this one. Both will be going to have the e power case at the same time minus. So then I write for the 0 to infinity. In terms of u of t, I take for the limit 0 to infinity. Then e power minus a j omega e power a plus j omega dt is equal to you make to do for the integration, then e power minus a t j omega t divided by minus of a plus j omega t. The limit is present for the 0 to infinity. If we substitute for the limit 0 to infinity, we should get for the frequency response of Fourier transform is equal to 1 by a plus j omega one side real exponential signal. Now we should write for the expression the Fourier transform condition of one side real exponential signal f of e power a t u of t is equal to 1 by a plus j omega, or e power a t u of t Fourier transform of 1 by 1 a plus of j omega we write. Okay, next. So we got for the x of omega is 1 by 1 plus of j omega. So we need to represent for the this mathematical expression as a graphical cases. So that's why we must need to find for the magnitude as well as the phase response. So for the Fourier transform of one side real exponential function is given by x of omega to 1 by a plus j omega. Now you multiply it by the rotational factor. That means the rotational factor is represented as a plus minus of j omega and a plus of j omega. Then we should multiply by both. What will be going to happen? So it's going to represent for the x of omega equal to a divided by a square plus omega square plus j omega divided by a square plus omega square. This is equal to 1 by root of a square omega square angle of tan inverse of omega divided by e. This is represented as a magnitude as well as a phase spectrum condition. The magnitude and phase spectrum Fourier series of signal exponential function is given by magnitude is equal to mod of x of omega is equal to 1 by root of a square plus omega square. Then for all value of omega, then phase angle I should write as a angle of x of omega equal to minus of tan inverse of omega divided by a for all value of omega. The graphical representation of single side or one side real exponential function with a magnitude and a phase response is represented as one side exponential condition is represented for the only one side. It will be going to have a maximum amplitude is 1. This is going to continuously with infinite time. It's not going to touch with the line. Next case, magnitude response is the Gaussian function is similar to the bell shape of curve. So, but the amplitude it's represented as a 1 by a. Then the phase response we represent by the phase responses. The amplitude is equal to pi by 2. Then this amplitude is equal to pi by 2. We make to join for the both the line. We got for the cutted over the graphical representation. Now this graphical representation of phase response, some of the term it's getting to decrease. After that it's go for the constant. So here also we go for the constant. Okay. So now both the condition we got it, magnitude response as well as a phase response for the one side real exponential signal. Next case we go for the Fourier transform of two side real exponential signal. What's the meaning of two side? It's going to possible to do for the right side as well as a left side of your plane. Two side real exponential function x of t is equal to e power minus a mod of t. Why we are taking the mod of t? Because of both the sides are equal, the negative as well as the positive side. That's why I write for the two side or double side real exponential function is defined as e power mod of a t, that is e power minus of a mod of t equal to e power a t for t less than of 0, e power minus a t for t is greater than of 0, e power a t u of minus t plus e power minus a t u of t. The function u of t and u of minus t are the unit step function and unit interval, that is time reversal unit step function, that is called for the unit interval. We represent by the time reversed unit step function. For the definition of the Fourier transform, we write for the x of omega equal to minus into plus into x of t e power minus j omega t dt. So this due to the x of t, we should substitute for this value e power minus a t mod of t. Then my integration of minus plus into e power minus at e power minus j omega t. But both the term is represented as a exponential case. That's why I should write as a mathematical model. X of omega equal to minus into plus into e power minus at u of t, e plus of e power minus at u of t e power minus j of omega t dt. So this value we need to do for the integration. We should get for the output after substituting for the limit x of omega is equal to 1 by a minus of j omega plus y of omega. That case y of omega case is represented as a another sequence, that is first sequence x of omega 1 by a minus of j omega. Another sequence is represented as a 1 by a plus of j omega. Now we can simplify for both. We got for the x of omega equal to 2a divided by a square plus omega square. The Fourier transform of two-side real exponential function is represented as f of e power minus a mod of t is equal to x of omega. That value equal to 2a divided by a square plus omega square, or e power minus at, that is t is present for the mod Fourier transform 2a divided by a square plus omega square. Then we need to do for the two-side real exponential signal for magnitude as well as a phase response. We take for the magnitude response x of omega is equal to 2a divided by a square plus omega square for all value of omega. The phase response angle of x of omega equal to 0 for all value of omega. The graphical representation of two-side real exponential function with its magnitude and the phase response is the real exponential function. I should write here the maximum amplitude is equal to 1. Why? Because of our case of x of t is equal to e power of minus a mod of t. This term is represent by the e power minus, that is e power at u of minus t plus e power minus at u of t we represent. So now the magnitude response is a maximum. When the t is increased, automatically is going to decrease the exponentially decreasing order. For the t, the negative side, t is going to decrease. Sorry, t is increased, the amplitude always going to decrease as a exponentially decreasing order. Okay, both it will be going to have possible. Then we take for the magnitude response. You should write for the frequency as well as the magnitude function. We get for the Gaussian bell curve shape, but the amplitude, maximum amplitude is equal to 2 by a. Next case, we take for the phase response. In this phase response condition, there is no imaginary part is present for the two-side real exponential signal. That's why the phase response always present for the 0 in the frequency state. These are the reference we taken from for the Fourier transform condition. Here we studied for the mostly in the Fourier complex function, Fourier complex condition. So up to this much, I'm going to complete my section. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.